There are many theories about the origins of Jupiter. Here's what we think happened. Nearly 5 billion years ago, a star in our galaxy exploded. The explosion caused a nearby cloud of gas and dust to collapse and flatten into a spinning disk. Most of the gas and dust collected into a hot, dense core that became our Sun. The remaining debris formed the planets and other small bodies in our solar system. And the majority of that debris came together to form the giant planet, Jupiter. Of all the 8 planets, we believe Jupiter formed first. Understanding the formation of Jupiter is essential to understanding the origins of our entire solar system, the formation of Earth, and the most basic foundations of life as we know it. Jupiter is 1,300 times the volume of Earth, more than twice the mass of all the other planets combined, the 5th planet from the Sun, and the largest planet in our solar system. Because of its enormous size and powerful gravity, it is believed that Jupiter has influenced the formation and evolution of the other bodies that orbit our Sun. Unlike Earth and the other smaller planets, the composition of Jupiter has remained unchanged since the solar system began. Like a time capsule, Jupiter can help us reconstruct nearly 5 billion years of history. Mission Juno will help prove or disprove theories about the types and amounts of materials that contribute to the composition of Jupiter. By peering beneath its clouds and discovering what Jupiter is truly like, Juno will also test our ideas about the formation of planets, as well as other major secrets of our solar system. Measuring the amount of water in Jupiter will help us understand how and where in our solar system the giant planet formed. Mapping the gravity and magnetic fields of Jupiter teaches us about the planet's hidden interior and whether it has a solid core. In our quest to unlock the history of the planets, Jupiter is the gateway, and Juno holds the key. Hundreds of scientists and engineers in 5 countries have been working for more than 10 years to design and build the Juno spacecraft. This solar-powered probe will travel 400 million miles into space with instruments uniquely built to withstand deadly radiation and the fiercely cold environment of Jupiter. Juno will conduct an unprecedented examination of the atmosphere, the interior, and the vast magnetic field of the giant planet. On August 5, 2011, one of the world's most powerful rockets is set to take off. The Atlas V 551 rocket, weighing 650 tons, launches and reaches a top speed of 4,500 miles per hour. The rocket hurtles through Earth's atmosphere, exhausting its fuel and reaching orbit in just over 10 minutes. The payload fairing falls away, revealing the Juno spacecraft within. Once in its proper orbit, the Centaur booster gives the probe its spin and sets Juno free on its journey to Jupiter. In the shadow of our planet, the spinning Juno spacecraft deploys its 3 massive solar arrays, which will power the mission for the next 6 years. After these arrays lock into place, power from the Sun streams into the circuits of Juno for the first time. Escaping the gravitational pull of Earth, Juno is still held to its trajectory by the Sun's gravity. The Juno spacecraft is carried 50 million miles into space, as far as the orbit of Mars. A burn from the main engine directs Juno back toward Earth for a final encounter with its home planet. Using Earth's gravity for energy, Juno slingshots into space, increasing its speed and receiving the boost it needs to pull away from the Sun and coast all the way to Jupiter. In the shadow of our planet, the spinning Juno spacecraft deploys its 3 massive solar arrays, which will power the mission for the next 6 years. After these arrays lock into place, power from the Sun streams into the circuits of Juno for the first time. After 5 years of being alone in space, Juno approaches Jupiter and begins reaching a top speed of 160,000 miles per hour, officially becoming the fastest man-made object in history. The main engine ignites to slow down the spacecraft, and Juno is captured by the powerful gravitational pull of Jupiter. Settling into the most challenging orbit ever attempted, Juno will come as close as 3,100 miles to the planet's cloud tops. Juno will continually duck below deadly radiation belts as it studies Jupiter in unprecedented detail for more than a year. Juno will use remote sensing to inspect Jupiter from its innermost core to the outer reaches of the magnetic bubble the giant planet inhabits. Juno will be the first probe to visit the regions above the poles of Jupiter, witnessing energies in the magnetosphere that create its extraordinary ultraviolet auroras. After orbiting Jupiter for over a year, the Juno craft will dive deep into the atmosphere and burn up. But the mission will never truly end. No matter how many answers we find, there will always be more questions. Our search for understanding and meaning continues.
I've been asked in to help with the gravity science experiment. Measuring Jupiter's gravity depends on measuring changes in the spacecraft velocities that goes around Jupiter. What we're looking at is for variations in that acceleration rate. That tells us something about the change in the gravitational field of Jupiter as it gets closer to the surface associated with a mass structure inside. And so what we're trying to do then is measure the spacecraft's velocity as a function of time very, very accurately. And we do that by measuring the Doppler shift of the radio signal. So if you've ever heard a fire engine going by with its siren, as it's approaching you, it's high pitch, and then when it goes by, it goes, right? That Doppler shift, that change in pitch, tells you about the velocity of the fire engine relative to you. So the instrument that we use is sort of a combination of the listening on the ground to the radio signal and the radio signal transmitted by the spacecraft. So the biggest part of the instrument, of course, is a 34-meter diameter radio antenna at Goldstone, California. Then on the spacecraft, there's a high-gain antenna that's pointed at the Earth. So the radio instrument measures the voltage coming in from the antenna from the Earth, and then it transmits a voltage that goes fed out to the radio signal to send back to the Earth. And then the gravity measurement tells us something about density variations, which then can tell us something about whether there's storms on the outside or whether they penetrate all the way through, and whether there's some hint of a structure at the center other than just compressed gas of the hydrogen.
JADE, the Jovian Auroral Dynamics Experiment, is a set of instruments that measures the electrons and ions. Those are particles, very tiny charged particles that are parts of an atom. And those particles actually produce the aurora. They follow along the magnetic field lines and they come down into the atmosphere at Jupiter, and they excite different sorts of interactions that emit light, different wavelengths of light. Those we observe as the aurora, but the aurora is really caused by these tiny, tiny particles coming down into the atmosphere. And JADE actually measures those individual particles. There are 3 identical electron sensors, and they look off in 3 different directions around the belly band of the spacecraft, so that they've got a broad field of view, 120 degrees wide, so the 3 of them actually can see all the way around the spacecraft all the time. The JADE ion instrument is different. It actually has a thing that looks a little bit more like a hamster wheel and a hamster cage, and that's to allow particles to come in over 270 degrees of observing angle, and twice per minute the Juno spacecraft spins around, and that allows that field of view to observe all of space. And so we're trying to understand what's the same and different between our own aurora and the aurora at Jupiter so that we can understand the processes really in detail for the first time. We'll be fully successful when we can come back and tell the world how it really works, what particles are involved, and why.
It's the Jupiter Energetic Particle Detector Instrument, and the acronym does not quite work out properly, but somebody loved the word Jedi for obvious reasons. We affectionately call our instrument the hockey puck because the main sensor is about the size and shape of a hockey puck disc. That hockey puck is sort of glued on or attached to a box which holds all the electronics associated with the sensor. JADE in particular works in very close coordination with JEDI So jade is measuring the lower energy part of the charged particles that are in Jupiter's environment. Jedi measures the higher energy particles. Those particles then go through the instrument and strike what's called a microchannel plate sensor. And a microchannel plate sensor amplifies the signal so that you get a current out the back end, and modern electronics can measure electric currents. We measure the radiation belts around planets. All the strongly magnetized planets have radiation belts. Jupiter has the most intense and interesting radiation belts. It's a rotationally dominated space environment or magnetosphere, where Earth is a solar wind-driven space environment. By studying two different environments that are powered by different things, you can begin to isolate the physical processes that are causing these variations. We hope to make great discoveries there.
A Jupiter infrared auroral mapper is an image spectrometer. At the beginning was meant for supporting auroral observations, to make images of aurora, and at the same time to look at the different view of the aurora. GRAM is made of two pieces. One part of GRAM is called the optical head, where is the sensitive part of the instrument that can focus the images, like a camera. And there is another box, which is the main electronic. And we can take images in two different wavelengths. One is devoted to the auroral observations, and the other part of the detector, the imager, it's sensitive to the thermal emission of the planet. So at the same time, we can take these two pictures that are superimposed, one above the other one, for observing the aurora if it's present. The reason why we are not with all the other instruments, but we are on a side in the aft deck of the spacecraft, is because we entered the mission later. So there was no more room in the big place, in the place where all the other instruments are. So we had to run quite fast to keep the pace with the mission.
JunoCam is on the spacecraft to take pictures of Jupiter, and we specifically designed it to get pictures of the polar regions of Jupiter. We've had a number of spacecraft that have flown past Jupiter and taken pictures, taken movies, but they've always been in the equatorial plane. And so this mission is the first one that we really get up over the polar regions. Let me mention that all of our pictures are of the cloud tops. Jupiter is a ball of gas, and all we will see are clouds. But they're very interesting, very dynamic clouds, so it should be fun. JunoCam is a unique element of the payload on this spacecraft because from the outset, its reason for being on the payload was to do outreach to the public. We do not have enough data volume to take a picture on every spin. We are going to have to be choosy and select what are the places that we want to take pictures of. We are going to invite the amateur astronomy community to send us their best data. So approximately a month away from when we take our data, we will be collecting the pictures from the amateur astronomy community and talk about why they would take a picture in any given latitude. And so the whole theme is to do science in a fishbowl. Let's do what we would do, but let's do it in a public forum so that the public can participate. And I'll be very happy if everybody gets involved the way I hope they do.
Years ago, the magnetic field provided a reference for navigation on Earth. So for 400 or 500 years, whenever ships crossed the ocean, they carried compasses so they could find their way when you can't see stars or landmass. A magnetometer is like a fancy compass. It measures both the direction and the magnitude of the magnetic field. So in this case, we fly a magnetic sensor at the very outer extremity of the spacecraft. We're on what's called a magnetometer boom, which is about 12 feet in length. It's about twice as long as I am tall. The primary purpose for our investigation is to map the magnetic field of Jupiter very accurately and try to understand how it's generated deep down inside Jupiter, in Jupiter's electrically conducting core. What we're going to do is make very, very accurate measurements in orbit about Jupiter and basically envelop Jupiter in a dense net of observations. And that'll give us the ability to image what the magnetic field looks like down in Jupiter's core where it's generated.
NASA loves acronyms, and so I just simply abbreviated microwave radiometer as MWR. From its name, it measures the radiation in the microwave region. Now that sounds like, a lot of highfalutin scientific terms, but it's really pretty simple. What we're actually doing is measuring the thermal radiation from the atmosphere of Jupiter beneath the clouds. And at every wavelength, we have 6 wavelengths on the instrument. Every wavelength is designed to look at a different region of the atmosphere, measure the thermal radiation coming up from some different region in the atmosphere. And by measuring them with the spacecraft, we'll be able to put that together into a picture, a three-dimensional picture of the atmospheric structure of Jupiter. What we've come up with as the most effective way to build an antenna is a big flat array that's about 5 feet square all the way around. It's as big as the side of a spacecraft, which is not a coincidence because we sort of sized the spacecraft to hold an antenna for our longest wavelength. Now, the other wavelengths are progressively smaller by factors of 2 at every step. So it turns out another side of the spacecraft can hold all of the rest. So we have no idea what we're going to see because nobody's ever seen this region before. It's going to be a surprise to all of us when we get the information back. So we expect to discover all sorts of new things.
UVS stands for ultraviolet spectrograph. It's an instrument that looks at ultraviolet light you can't see with your eyes. It's too short a wavelength, but it also breaks that light up into different colors, much like a prism would break up white light into a rainbow. It has 2 components to it, actually. One is the sensor, which is sort of a telescope plus a spectrograph side by side. And all the electronics, except what need to be right at the sensor, are put in another box, which is deep inside a vault, which on Juno protects all the sensitive electronics from the radiation at Jupiter. Jupiter has some similarity to Earth. The Earth has northern lights, auroras, and they're spectacular to watch. Jupiter's auroras are like 1,000 times bigger. So the auroral oval on Jupiter is bigger than the entire Earth and much, much more powerful. And it's always on, but it's much easier to look at it in ultraviolet wavelengths because we can see it on the day side as well. When we see light from those different colors in the UV, they tell us different things about Jupiter's upper atmosphere and the particles that are causing the auroras to happen. We'll be able to contrast how auroras work at Earth with how they work at Jupiter. And there are many differences we already know, but there's a lot of things we've never been able to see at Jupiter that we can see with Juno once we get there.
The WAVES instrument is basically a radio. It tunes to frequencies all the way from 50 hertz, which is near the bottom of the audio frequency range, up to above 40 megahertz, which is above the limit of the radio emissions that Jupiter generates. The WAVES instrument has 2 sensors. One is designed to measure the electric field component of these waves, and it looks like a pair of rabbit ear antennas that you might have had on a TV when you were a kid, except these are about 10 feet long.
The other sensor is a much smaller device. It's about 10 inches long, and it's basically a coil of wire. It has about 10,000 turns on it, and it's designed to measure the magnetic fluctuations of waves. So these two sensors are used by the receivers to study the various phenomenon, particularly in Jupiter's polar magnetosphere. For example, the maximum frequency of the radio emissions that we detect told us what the magnetic field strength was in the magnetosphere of Jupiter, long before any spacecraft arrived. Juno was designed to actually go to another planet and make the first measurements of an extraterrestrial auroral region in great detail. So I think we learn about ourselves by studying other environments in the universe.
ATLO is an acronym. It stands for Assembly, Test, and Launch Operations. Basically, we'll assemble it, and we'll do all the system-level testing, we'll do all the environmental testing, we'll do all the launch processing, and then we will go ahead and launch it.
So in ATLO, you basically start with a bunch of pieces. We had what was known as the prop module. That's the large base piece of the structure. On top of the prop module sits the vault. Individual boxes, flight computers, our power subsystem, all came in separate pieces. And in ATLO, our job is to take all those pieces and come up with a plan and strategy of putting them together in an organized manner that makes sense.
We have a philosophy at Lockheed Martin to test as you fly. We have to try to replicate the environment that the spacecraft is going to see in space.
So we basically trick it through another piece of software into thinking that it's flying. And so we run through all these scenarios, just like in flight, and we verify that it functionally does what it's supposed to do.
So in order to accurately represent all different environments that the spacecraft is exposed to, we need to kind of break up the tests individually. One of the more exciting tests that we got to run on the spacecraft was the solar array deployment test. We have very large solar arrays on this spacecraft so that once we get to Jupiter, we have enough electricity to operate the spacecraft. In order to be able to deploy them with low friction, we used a flat floor and a pneumatic device that's kind of like a hovercraft. A thermal vacuum test is probably the largest, most thorough, complete test that we'll do on a whole entire spacecraft assembly. So once we get the spacecraft fully assembled, we will put it in a large chamber that tries to replicate space. Also within the chamber is a shroud that is filled with liquid nitrogen, and it can get as cold as negative 180 degrees C. So we try to simulate what environment the spacecraft is going to experience in space.
So we get through these major environmental milestones, verify that the spacecraft is working as we planned, take it out, verify that it functionally works after we do all the tests, then we prep it to ship down to the launch site.
On launch day, of course, it's a dream to have perfect weather, no clouds in the sky, but we have to do with what we have. There are weather rules in place, weather criteria that we cannot violate. There are rules for cumulus clouds, there are rules for anvil weather clouds, there are rules for lightning within the area, within 10 miles, within 5 nautical miles. So there are several weather rules in place.
Atlas systems, propulsion, go. Hydraulics, go. Pneumatic,
Making
go.
a list to get through a launch countdown is the only way to get through a launch. And even once my list is checked off, I still won't throw it away because I want to go back and double and triple check to make sure that I did everything on that list.
As soon as we get the go-ahead from ULA, we will power up the spacecraft for the final time. We make our spacecraft dirt simple, so that at the end, there's very few things to go wrong in this very critical time. So our spacecraft is a very easy spacecraft to launch.
Juno gets to Jupiter by flying by the Earth. It gains momentum by passing the Earth at 500 kilometers altitude, and in doing so, it gets sucked into the Earth's gravity well. And what happens is that the trajectory, which is on a path relative to the Sun originally, now is flying by the Earth and is also influenced by the Earth's gravity field. It gets deflected out towards the planet Jupiter. The idea is that you can't get there directly unless you have a much bigger launch vehicle. When we get to Jupiter, we do a big maneuver called JOI. The Jupiter Orbit Insertion Maneuver is what actually puts us into an orbit about Jupiter so that we're captured by Jupiter's gravity. It needs to be a big maneuver because we're flying at this enormous velocity around the sun, and in order to be captured by even a big planet like Jupiter, we have to aid that capture by doing a big maneuver to slow us down. There's so little time to react that we have to let it do its own thing and just trust that the planning and the testing that went into that will do the right thing. We plan on actually listening in on the spacecraft as it does its Jupiter orbit insertion. And at the very end, we have it radio back to tell us, okay, we did all the right things. Here's how the spacecraft is doing. We survived.
One of the great excitements about space exploration is it's a big public endeavor. Everybody's involved.
There's some wonderful amateur astronomers who are very knowledgeable about individual storms and clouds on Jupiter.
I think the public involvement in these missions are really what makes it important and exciting and fun. If it was just us scientists looking down our own microscope, it wouldn't be so much fun.
The public will see how we make decisions and what we care about.
They'll continue interest in science, they'll ask questions, they'll be curious. I think this is an important part for society to think about what's out there and how it works and how it all fits together.
Not only do our capabilities complement each other, but our enthusiasm infects each other, and it's a very good collaboration with the amateurs.
I, as a 14-year-old, stayed up until 4 a.m. to watch the guys walk on the moon. And I expect there will be kids who will be following everything that's happening with Juno. It's a great privilege to be involved with something where the public are all actively interested. Yeah, it's fun.
This is Atlas Launch Control. We are now 2 hours, 32 minutes, 32 seconds away from the liftoff of the Juno spacecraft aboard an Atlas V rocket. Liftoff is from Launch Complex 41 at Cape Canaveral. The forecast is essentially unchanged from what we've been watching all week. There is just a 30% chance of not meeting the launch weather criteria.
It takes everything we know to get off this planet. So while everything that NASA does and building the Juno spacecraft and exploring Jupiter is all high tech, I think a rocket launch represents the extreme of that edge.
The energy in the room on launch day is stressful, but in a good way. It's a good feeling. It's almost electric. Everybody's excited and nervous, and I've seen people before, biting their nails.
A rocket launch is one of the most amazing things to see. I mean, it's truly a cosmic event.
OSM. Go. ULA safety officer. Go. Range, weather, and final clear to launch.
Go. LC, LD, channel 1.
Go ahead.
LC, you have permission to launch.
Roger.
A launch is probably our single biggest risk in the entire mission.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
When you see it, the first thing that you're impressed with is just the amount of energy. You feel it because the ground is shaking and you're miles away and the waves are going through the ground like an earthquake would.
Mach 1.
You're canceling gravity. Gravity's pulling you down. You've got to get to a certain speed, and then that's the escape velocity to leave the Earth.
Max Q. Boosters throttling up. We're on schedule. Engine response looks good.
You're watching something going from one planet to another.
And we have solids 1, 2, 3, 4, and 5 jettisoned. Visual indication that all solids have separated well. Current altitude is 45.8 miles. In altitude, downrange distance 69 miles. Velocity 5,413 miles per hour. And we have payload fairing jettison and CFR jettison. We have retros and spacecraft separation. This concludes the plus count commentary for the AV-29 Juno mission.
We communicate with the Juno spacecraft with radio waves and radio frequencies. But what we do is we send up commands or data to the spacecraft to tell it what to do. It in turn takes data and sends back what we call telemetry.
The way that we find out if there's a problem on the spacecraft in space is by monitoring our telemetry. And our spacecraft talks to us on Earth through the Deep Space Network.
The Deep Space Network is a set of antennae that we use that are around the world in order to return data to us and to send commands up to the spacecraft.
We've designed a lot of points on the spacecraft that tell us things like the state of charge of the battery and what temperature things are at. And we look at that telemetry and monitor if the spacecraft is happy or sad and doing well or not. And we set limits on that, so it will give us automatic alerts if something's wrong. And so on the ground, we can look at it and make sure everything's okay. We can detect a problem that way. The primary way that we detect problems on the spacecraft is we make it smart enough to detect them on its own. So the spacecraft has a system called fault protection.
It's constantly looking for how the spacecraft hardware and software is operating. Is everything going per plan? Do we have anything that's not operating as expected?
So if we're spinning and the spin rate gets out of control, a fault protection is looking at the spin rate and determining, okay, this level of spin is okay, and if it gets past this number, I'm not happy. And so if it gets to a number that it's not happy, it will take action.
It actually will take care of it itself, and then after it's reconfigured or whatever, then it'll send down the information and let us know that that's what's happened.
Or if it can't solve a problem or the problem is too large, it will put it in safe mode and basically say, okay, I'm just going to wait for the ground to help me because I'm confused.
Nothing should cause a further problem for the spacecraft. We shut down the instruments, we shut down other aspects of the spacecraft, and we make it kind of operate very simply at a very low data transfer level so that when the Earth picks it up, it's very apparent to us right away that it's had a problem, and we can then start fixing it right away.
The spacecraft would continue to operate after it experiences a particular fault. One particular fault will not result in a total failure of the spacecraft.
Our little spacecraft these days are very complicated, and they're very smart. They know how to take care of themselves.
So in a lot of ways, the most innovative or dramatic thing about Juno is the orbit. We're going to orbit Jupiter in a way where we get to go very close to the planet, inside the radiation belts instead of outside the radiation belt. We're in a polar orbit, so by small adjustments of the timing, we can map the entire planet. We can get repeated stripes at different longitudes as Jupiter spins underneath us.
It does mean that Juno is going to see the polar regions to a greater extent than with other spacecraft. But I think the most important thing is that it gets in very close to the planet as part of that ellipse. Brings it in a few thousand miles above those cloud tops, very close, near the equator.
We're going to go over the poles of Jupiter. That means we can study the magnetosphere in a different way. Where all the magnetic field lines come together, we get to see from Juno. This is the first time we're really using passive microwave radiometry and multiple channels to try to study the composition of an atmosphere, especially a giant planet like Jupiter. And that's new and unique. But in some ways, the most unique part of the Juno mission, the thing that really makes it stand out, is just the orbit.
An aurora, as we see it on Jupiter or on the Earth, is caused by charged particles, electrons or protons, crashing into the atmosphere.
When those electrons come bombarding in, they excite the electrons inside the hydrogen atom, and UV light comes pouring out, and that's what produces most of the aurora on Jupiter. This is very similar to the northern lights of the Earth. It's the same physical process.
Deep inside the planet, the hydrogen has been compressed so much that it loses its electrons, and you have a conducting layer. So people call this metallic hydrogen. And it's in that conducting shell that we think Jupiter generates its magnetic field. Now, one of the interesting things is that it's carrying with it electrons and protons that are spiraling around as they crash into the atmosphere at the north and at the south. And when they do that, they create what we call an aurora because they're generating light. It's quite a spectacular sight if you can see this aurora going on. It's so bright that you don't have to be on the surface of the planet where this is happening. You can look at it from the outside. And Juno is equipped to look at the aurora on the north and south poles of Jupiter and to study it in a way that has never been possible before.
A magnetosphere is the sphere of influence of a magnetic field. So a planet that has a magnetic field has a magnetosphere when its sphere of influence extends beyond the planet out into space and affects the region around it.
The presence of the Earth's magnetic field was recognized back in the 14th or 15th century, and since the 17th century, it's been a topic of active study. Yet we still don't really know how magnetic fields are generated inside planets.
The magnetosphere of Jupiter is vast. So if you think of Jupiter being 10 times the size of the Earth, and the magnetosphere is 100 times the size of Jupiter. So this is vast, a big, big, big volume.
By measuring Jupiter's magnetic field from Juno, we hope to do two things. One is to advance our understanding of how magnetic fields are generated in planets, and the other is to learn about the interior structure of Jupiter. You might question why go 400 million miles to Jupiter to study its magnetic field when the Earth has a perfectly good magnetic field which we could study. Jupiter's metallic hydrogen core is much closer to the surface. So when we measure Jupiter's magnetic field from Juno, we're much closer to where the magnetic field is generated. And by looking at the magnetic field, we should be able to tell whether Jupiter has a solid inner core. And that has profound consequences for how Jupiter formed, for models of its interior, for understanding its gravity field. It's a sort of key observation we'd like to pin down for Jupiter.
The rings of Saturn are very well known. They're this gorgeous set of rings circling the planet. These rings are made of ice crystals, and that's one of the reasons that they're so bright and that they're so easily seen. It turns out that Jupiter also has rings, but these rings are made of dust, so they're hard to see. In fact, they were only discovered by the Voyager spacecraft. Before that, we didn't know that Jupiter had rings. They're caused by small satellites that Jupiter has moving around the planet close in. These satellites are releasing some dust from their surfaces, and that dust forms the rings. That's why they're so difficult to see from the Earth. When you get close up with the spacecraft, they're obviously easier to see. You might worry about Juno running into some of these rings as it makes its orbit, but it doesn't. The orbit is oriented in such a way that it will not pass through these rings.
The reason we plan to crash Juno into Jupiter at the end of the mission is for what's called planetary protection.
We can't make the spacecraft perfectly sterile. We try to keep it as clean as possible. We spend quite a bit of effort, dressing up in bunny suits and putting in a clean room that's changing air as fast as we can do it and trying to keep it as clean as possible, but nothing's perfectly clean.
The United States is part of an international treaty that says we will be sure not to contaminate other worlds that could potentially harbor life.
There are some moons around Jupiter and Mars and other places that kind of look enough like Earth that we're thinking, well, maybe there is a life that we would recognize there.
You would really hate to 50 years from now, send a mission to, say, Europa, one of the moons of Jupiter, and find life and then not be able to tell whether this is Europan life or contamination from Juno.
So what we do is we dispose of Juno when we're done with it, and we let it burn up in Jupiter's atmosphere.
There's about a 99% chance that what would eventually happen to it is it would crash into Jupiter, burn up, not contaminate anything. But 99% chance isn't good enough for us. It isn't good enough for NASA. We need to show by agreement with NASA that we have a less than 1 chance in 10,000 of contaminating Europa. So while we still have control, before the radiation has done any damage, we'll fire the rockets, we'll burn Juno up in the upper atmosphere of Jupiter, and that way we'll be certain we're not going to contaminate anything.
Jupiter has such a strong radiation environment that when we send all our sensors in to do their observations, there's a lot of challenges that have to be overcome to make sure that they can do that, particularly with noise. All the high-energy electrons and protons in the environment whiz through the instruments and create noise in the detectors and sensors. That kind of condition can be a catastrophic event for a device. It can destroy it. So that's one of the radiation effects that has to be screened and understood when you're designing an instrument. Testing for the Jovian radiation environment on Earth is not easy. You have to go to a very high energetic electron facility, which is a very rare type of facility on Earth for this kind of testing. It's not something that's commonly done. People don't do space missions to Jupiter very often, so there isn't a big customer base for that. We've ended up going to facilities and hospitals that treat cancer patients, or other facilities that are used to simulate nuclear blasts for submarines. Very unusual places in all different parts of the world in order to mimic the Jovian radiation environment. Right now, we're looking at how we can understand what the environment is actually doing to our instruments while we're in flight. We've modeled it, we've tested, we have a good idea of what will happen. But we can understand from the instrument telemetry and the science return exactly what they're experiencing. If there are certain failures or graceful degradations, that will be visible in that data stream coming down. The very extreme radiation environment, very changing radiation environment, and other missions in the future will go to these locations and they will design based on what we'll be learning.
The short answer for why Juno is solar-powered rather than nuclear power is because we can. At the time we did the proposal for Juno, NASA had generally speaking, a policy that it's okay to use nuclear power to do things in space where you need to use nuclear power. But if you can do something simpler, like solar panels, you should.
We decided it was probably less risky to advance the technology of solar cells to work at Jupiter than it was to invent a new nuclear power source.
We haven't taken solar panels that far before and run an entire spacecraft that far from the sun off of solar power.
We had to work at a colder temperature, we had to work with less light, and we had to be able to work inside of a radiation environment, so as things got damaged, you had to either protect them or make them more efficient.
The biggest design challenge of the solar arrays was probably just their size. Each solar array is 28 feet long, and so we have 3 of them. And so when the solar arrays are fully deployed, the Juno spacecraft is almost 60 feet in diameter across the solar arrays.
Getting those big solar panels to work the way we expect them to work and produce the amount of power we need, that's been a bit of a challenge.
The solar arrays are pretty interesting. When we deploy them, they'll be generating about 12 kilowatts of power. As we get further and further from the sun, that amount of energy will drop off until we finally get to Jupiter, where we're only generating 400 watts. It's not even enough to run a hairdryer.
Generally, with space exploration, you're pushing the envelope of technology.
Solar panels have improved a bit. The instruments have improved a bit and can run on less power. And I think it's turned out to be a very good decision for Juno.
The design of Juno and the science measurements that we wanted to make were all taken into consideration at once when we were trying to figure out how to do this the most efficient way. So Juno has 3 solar arrays that stick out. It could have had 4 or 5 or any number. We looked for something that was efficient and could be packaged inside of a rocket. That was one of the first requirements. We also wanted to carefully make it so that the science instruments could look out between the solar arrays. We knew we were going to have to see a certain, what's called a field of view. I wanted to be able to look up and down the magnetic field lines as we flew over Jupiter so I could see the particles that were creating the aurora.
When we come off of the launch vehicle, we're spinning at about 1.4 RPM. When we do our burns, we spin up to about 5 RPM to give us a little more stabilization. And when we're going around the planet, we're spinning at about 2 RPM.
Juno spins like a propeller, where the propeller's kind of facing the sun because they're all solar powered, and we want to have each of the instruments to be able to look out between the solar arrays and see Jupiter or wherever they need to look in order to do their science objectives.
There's 2 basic reasons why we want to have a rotating spacecraft. One is really simple. It's just stable that way. If you spin something, it stays spinning. It's like a gyroscope. We call it a simple spinner, a spinning spacecraft. The other reason is we can use a spinning spacecraft to let each instrument get its turn to see Jupiter.
If I had only one sensor looking in one direction, because I was spinning twice a minute, you'd think I'd be able to look in all directions every half a minute. But I'm moving so fast going over Jupiter that in fact I'm going to pass the field lines that are making the aurora, and I might only be looking up or only looking down or looking sideways by mistake. And so by putting 3 sensors around, looking all the time between the solar arrays, we ensure that no matter how fast we go across, we're looking in the right direction to make our measurements.
But once the whole spacecraft gets put together, it's important for us to operate it in a flight-like way. So we enact a policy on our missions here at JPL called Test As You Fly. We say, okay, we're going to pretend that we're launching the spacecraft today, and we set the universe simulator in the clean room to pretend it's launch day.
Juno has a very complex instrument suite. The instruments are tested both individually at their home institutions as well as part of the flight system on the path towards launch.
We try to replicate both the conditions, the timing, the personnel, the procedures, the products, the hardware, everything, similar to what we would have actually in space when we're flying.
We will go through acoustic energy testing to make sure that the instruments will be able to withstand the launch environment. We'll go through a thermal vac test where we'll simulate being in a vacuum in space.
We pretend to fly the mission on the ground, and then we make sure we understand the differences between the environment we have on the ground and the environment we have in space.
It's a blast to march through that testing suite and make sure that you've thought of all the contingencies and tried to break it and make sure it's going to do what it needs to do.
What is the Great Red Spot? It's a swirling mass of gas and colored clouds that is bigger than the Earth. It's been around since the telescope was invented. Maybe it's much older than that even. People sometimes call it a hurricane, but it's probably different from a hurricane in the way it works. There's no ocean underneath, and it's much bigger than a hurricane, and it doesn't have any intense eye at the center. The red spot is rolling like a ball bearing between 2 conveyor belts. Just to the north of the red spot, there's a westward moving jet stream. And just to the south of the red spot, there's an eastward moving jet stream. Somehow the jet streams steady the red spot and keep it trapped at one latitude. There's no solid surface with which to measure your wind speed. It speeds up and slows down slightly. It's not anchored to anything. It's on its own schedule.
The interior of Jupiter is a tough problem for us. To get deep inside, we have to use indirect methods. We can't go there.
We think that Jupiter has a core, but we don't know for sure. It is nonetheless likely to be perhaps 10 times the mass of the Earth. It may not be solid. It's very hot.
The pressure is too great. The temperature is too high. It's just too far in. We can't get there. So what we have to do is to use radiation that's coming to us from those lower depths to tell us what's going on down there. And this is where Juno comes in.
Juno is exciting because we will learn such a wide range of things. For indeed, Jupiter is the most massive planet in the solar system. It is the body you want to understand in order to understand the architecture of everything else, including Earth.
What is the proportion of water on Jupiter compared to the amount of hydrogen on Jupiter, and how does that compare with the proportion of hydrogen to water in interstellar space and in the sun? That's a very important question, and that's one of the things that Juno is going to address directly.
I would expect Juno to tell us more about how planets work, meaning how the heat gets out, what kinds of flows exist inside the body, how magnetic fields get generated, learning what Jupiter is made of, and learning about how it works. Those, to me, are what make the Juno mission exciting.
One of the most exciting aspects of weather is a thunderstorm. So what happens on Jupiter? We know that lightning occurs on Jupiter. The Galileo orbiter made images of lightning on the night side of Jupiter. And these lightning bolts are hundreds of times more powerful than lightning on the Earth. In a way, this is surprising because Jupiter gets less sunlight, less energy from the sun than the Earth does because it's much farther from the sun. With Juno, we want to understand the structure of these thunderstorms. We want to understand where these parcels begin to rise, how much water is in them, how they're organized, are they larger than terrestrial thunderstorms, and why it actually has thunderstorms and super lightning. Juno will be able to tell us that.
When I was younger, I was always fascinated by astronomy, and I can remember just looking up in space and looking out at the stars out there, wondering what was out there.
I actually wanted to be an aerospace engineer even when I was a little girl. I really liked math, and I liked, space and astronauts, and I would write letters to the NASA centers and get pictures and stuff.
I had posters in my bedroom of Jupiter and Neptune and Saturn. I thought they were just amazing.
As a little kid, Jupiter was my planet.
I would look out there, and you couldn't touch it. You couldn't learn about it enough because you couldn't get there. And so I always had this yearning to want to reach out.
And when people would ask me, what do you want to do when you grow up? I said, I want to work on spaceships.
I really wanted to work on rockets and build things that would go into space.
And it's just really exciting to have a chance to do something that I really wanted to do when I was a little kid.
For whatever reason, I got lucky and I'm the head of Juno, and I'm reaching out. And of course, I could never have done it myself. It's only through everybody reaching together that we can reach it all.
It started out on the back of an envelope, as many things do.
It's amazing being able to see a vague notion that you have in your brain turn into a real piece of hardware that is going to fly all the way to Jupiter.
So Juno is really an incredible international mission. It's a very large mission, involves people from many, many different countries, scientists, engineers, administrative people, technicians, people who do purchasing. I mean, it's amazing how many people in different walks of life have to be involved in making a mission like this happen.
It's a big public endeavor. Everybody's involved.
We really have the A-team here, and it's amazing that when you get that kind of atmosphere and that kind of collaboration and synergy, how that can just make the whole thing, even the hardest problem, that much more palatable.
We check our egos at the door, we roll our sleeves up, and then we just dive in and work whatever needs to be worked.
I think that it's a tremendous experience to be involved in something where we can learn about how planets formed.
We ask why are we here, where do we come from?
Jupiter is the place to go to understand our origins, how the solar system formed, how the Earth got its water and organic molecules, and whether we are a typical planetary system in the cosmos.
You get to open a door that's never been opened by a human before.
You're sending something to someplace where few things have ever gone.
When you work on a project like Juno, which is really exciting and there's a lot riding on it, a lot of people working on something that takes a long time to prepare, there's an opportunity to be really anxious, there's an opportunity to be really excited. you can worry about all kinds of things.
In a way, it's like having a child. You rear this child throughout the years, and then all of a sudden they take off on their own and they become independent.
It feels a little like an unruly teenager that I'm ready to get out of the house.
Some of those cameras really do feel like my babies that I've been working on for such a long time. It's going to be really wonderful.
We developed the design for the spacecraft, we put it together, and we let it fly.
There's nothing like listening to that launch vehicle take off and watching something that you built and poured a lot of time and energy into leave the planet.
You know that the whole team's done everything they can to ensure mission success, but there are no guarantees. So I think pretty much everybody holds their breath and just waits.
I think it's starting to hit all of us how close we are, and this is really going to happen.
I'm excited to see this thing go and shake people's hands and walk away proud of working this mission.
I don't know what else in life that you could do that will be so exciting and so different all the time, and again have such job satisfaction.
It's very rare to see a team that knows how to work together the way that this team does.
It's quite a privilege and honor to be able to perform in this role.
This is certainly the best job I've ever had, and I love it.
It's such a fun job, and it's really a wonderful way to make the world seem even bigger than it is.
In Roman mythology, which of course is rooted from Greek mythology, Juno was the wife and sister goddess of Jupiter, or in Greek it was Zeus, and the Greek name for Juno was Hera. So they were companions, and Zeus, of course, was the king of the gods, and she was the queen of the gods, Juno. She was married and cared a lot about children and marriage and keeping everybody well-behaved and sort of like a good mother would. And Zeus was sort of being naughty with some friends and doing things, and he saw Juno looking down at him or starting to come close to him. So he cast a veil of clouds around himself and his friends and tried to hide his naughtiness. But of course, Juno was a fairly powerful god herself, and she saw enough that she said, okay, I'm suspicious, and kind of traveled down and used her powers to look right through the clouds and see the true nature of Jupiter and understand what he was really up to. And that's exactly what the Juno spacecraft does for us, is that it goes there with special instruments in a special orbit and uses its magical powers to see right through Jupiter's clouds and understand its true nature, which is holding these secrets for us about how the solar system formed and where we all came from.
Jupiter's by far the largest planet in the solar system. It has an influence on everything else. So if we want to understand how do planets form, how do solar systems form, we really have to start with Jupiter.
By studying Jupiter, you're going to get one piece of the puzzle. Not necessarily how life formed, but maybe how the ingredients that made up life eventually got spread around in the early solar system and got to us.
We care about the light elements because that's what we're made out of. We've got a puzzle about where these volatile elements, these lightweight elements like nitrogen, carbon, noble gases, where they came from.
To determine how much water is in Jupiter is essential to understand how this planet came to form and then how it influenced the formation of all the other planets in the system.
When the Earth formed, in the absence of Jupiter, it probably would have gathered very little water and organic molecules, which would have been concentrated in the colder outer part of the solar system. What Jupiter evidently did as it formed was to scatter cold material that contained water ice and organic materials to the inner solar system, where it could be captured by the Earth and the other terrestrial planets.
We learn about the origin of the solar system. We're learning about our own origins. We're learning about how life comes to be, about who we are and what our place is in the universe. It's about knowledge and about humanity's quest to understand. For me, that's why we need to study Jupiter and the solar system and almost everything.